Oh, okay. Okay, we're just going to continue where we left off. Last lesson, we did introduction stuff. So a lot of the things like how to name organic compounds, what are functional groups, stuff like that. Okay, for today, we're going to move on to something a bit more important. Okay, so you can turn over to page 31. Yeah. Okay, so on page 31, right, okay, before we touch on this segment, I'll give you a piece of paper, right? Just write down whatever that I have on the board now. Because the notes, right, didn't include something that's a bit more important. Okay, usually that one is, I think it's important enough, right, to go through because then it will help you understand this portion a bit better. Yeah, okay, I don't know where your school goes through this portion at lah. I don't know which topic because some schools are different. Okay, but we're just going to touch on this today. Okay, today we have two things to discuss. Okay, essentially, I just want to finish the set of notes here. Okay, the number one thing is hybridization of carbon atoms. Okay, the second thing we'll go through later, right, is this thing called isomerism. Okay, so once we finish this two, right, okay, we'll need another lesson next week to do the tutorial questions. Okay, we do all this without doing questions, right? Okay, we're just gonna dive straight into hybridization. That's my voice sound a bit like weird. Doesn't okay, weird. Okay, because it sounds very hoarse. I was screaming a lot last time. Yeah. Okay, so anyways, hybridization of carbon. We are specifically looking at carbon today. Now, this is one of the more difficult concepts that a lot of people tend to face. Yeah, okay, so when people start to learn this in schools, right, a lot of the times the school doesn't really go through this slowly. Okay, so they just speed through this, which is quite bad. Okay, but essentially in this segment, let me just show you what the problem is first. Okay, for carbon, what is the electronic configuration? 1s2, okay. 2s2n. 2p2, okay, so 2, 4, 6. Okay, must add up to 6 carbon, 6 electrons. Okay, so let's look at this thing first. Carbon has 6 electrons, but it has 4 valence electrons, right? Okay, you know carbon can form how many bonds? Okay, 4 bonds. Okay, that's a fact, right? Carbon can form 4 bonds, and that's probably because it has 4 valence electrons. Okay, so this is what we know, and this is what we've been taught since like secondary school. 4 valence electrons give you 4 bonds for carbon, which is not wrong, but until right, we look at atomic structure. Okay, earlier in the year, right, when we discussed atomic structure, right, okay, I want you to take a look at the electronic box diagram for the valence shell only. So as you can remember, right, 2s is like that, and then 2p because we only have 2 electrons. Okay, the electrons here are unpaired. Now, in atomic structure, what else did we learn? What kind of electrons can form covalent bonds? Is it the paired electrons or the unpaired electrons? Unpaired, yes. Okay, only unpaired electrons can receive another electron to form a bond, right? This one, how can they form a bond? So in other words, if from atomic structure we have learned this, carbon has 2 unpaired electrons, which means by right it can form how many bonds to it? 2. Which is weird, right? Because we know for a fact that carbon forms 4 bonds. But based on what we learned in atomic structure, which isn't wrong also, having 2 unpaired should only give you 2 bonds. So now you can clearly see, right, there is a discrepancy between 2 theories. So carbon in fact forms 4 bonds, but based on our atomic structure theory, it doesn't. So that's why, right, the only theory that can reconcile this idea is hybridization. When we discuss hybridization, this idea will help to address these problems. Okay, so that's like a bit of a background, and I think it's good to know this also. Okay, and beyond that, right, okay, there's also stuff that's not in the notes, so I'm just gonna go straight into it. Okay, but so far, okay, right? Now, what we're gonna do is I'm gonna draw a very familiar looking diagram. Okay, an energy level diagram. Okay, and in this diagram, right, what I'm gonna do is this. I will plot all the energy levels of all these orbitals. So in other words, it's very simple. In 1s, okay, you just have the 2 electrons here. 2s is much higher because it's in a different shell, right? Different shell, higher energy level. How about 2p? Okay, 2p as you can see over here. Okay, let me draw 2s way higher. So let's illustrate a few ideas here. Okay, 2s is higher. 2p is only slightly higher. As you can see, these are the arrangement of the electrons, right? Now, first thing you can notice first, from the 1s to the 2s, is the energy gap very big or very small? Very large. Okay, so you can write it down first. Okay, the energy gap here is very large. Whereas from 2s and 2p, what is the energy gap? Okay, in comparison, it is very small. Okay, good. Now, this has a huge part to play in the bit. Okay, so let's take a look. The energy gap between 2s and 2p is small. What does that mean? Now, another thing is this. Electrons, are they always moving or are they stationary? Okay, electrons are always moving, right? Okay, they are they're just jumping around about everywhere. So if you can take a look at 2s and 2p, you should be able to look at it as like that. Because the energy gap between 2s and 2p is very small, is there anything stopping the electrons from just oscillating between the two levels? No, because as we mentioned, electrons always moving. So in other words, all these 4 electrons, you shouldn't be doing it as 2 electrons on 2s, 2 electrons at 2p. In fact, you should be looking at it as 4 electrons across both 2s and 2p orbitals, subshells. Does that make sense? Okay, so 4 electrons just oscillating in this entire system, right, between 2s and 2p. It shouldn't just be strictly 2 here and 2 here. So what does that mean? Okay, because electrons can exist between both of these levels, they can actually come up with a level that is in between these two. So in these two, in between these two levels, you can see this. There's 1s and 3p, correct? We're gonna equate all of them together. In other words, what I've just done is that I have now placed these 4 orbitals on the same level, on a level that's somewhere in between the 2s and the. Now, why am I able to do this? Because yet again, the energy gap is very small, and that's why they can pretty much reach like an average. You can see the idea there. It's like the average between 2s and 2p, since the electrons are existing between both of these levels anyway. So, now that we have 4 orbitals on the same level, I just need you to take a look at this very cool thing, right? Okay, so 2s only has one, okay, there's an s orbital, right? But the p got 3 p orbitals. Right? So there's a P here, P here, and P here. Now we know from atomic structure that this is Px, Py, and Z. I'm not really concerned with that now. Just need to know there are 3 orbitals. Now that they're all on the same level, how do I arrange all these electrons? I have 4 electrons. How should I arrange them? What do you think I should do here? Okay, just now I'm doing like that. I have to put them singly first, then I pair them up, right? Then afterwards, I need to put them singly first. But over here, now that they are all 4 orbitals on the same level, how do we arrange 4 valence electrons here? Yeah, 1 each. Okay, 1, 2, 3, 4, right? This is what we normally learn. We have to fill them up singly first. So can you see, right, that this actually addresses the issue that we saw just now. We mentioned that there are only 2 unpaired electrons. That's why you should only form 2 bonds. But because of hybridization, the orbitals, right, can actually combine together. 2s and 2p orbitals can combine, right? And this is how it looks like. 1s combined with 3p, you will form this new orbital called a hybridized orbital. sp3 hybridized orbital. Because now that they are all on the same level, this one also same thing, all of them will become a combined new orbital, which is your sp3 hybridized. Okay, so now there's no such thing as just s orbital and p orbital. Now, right, we learn a new type of orbital, which is just a combination of both the s and p orbitals together. Again, why can they do that? It's because the energy gap is very small. They both exist pretty much at the same time. So we can like combine them together to form these new types of orbitals. You know what hybridized means in English? Hybrid is to combine together, right? So it's the same idea over here. These guys are called hybridized orbitals because you take certain s subshells and certain s orbitals and p orbitals, combine them together to form this new hybridized orbital. Can see that? So in other words, you have 4 unpaired electrons. It addresses the issue that we had at the start. And at the same time, let's take a look at how this looks like. Okay, so let's lay down a few facts as well. Okay, so remember, right, for carbons, we have sigma bonds and we have pi bonds, right? Okay, sigma bonds, how do they form? How do the orbitals overlap? Head-on. Okay, good. So let's just write down all these facts again, then we can link that to this. So head-on overlap of orbitals, right? But let's lay down another fact. Sigma bonds are formed, right, from the head-on overlap of hybridized orbitals. In other words, the orbitals that I have just newly formed, these guys can only overlap head-on to form only sigma bonds. So just highlight these things now. These are some facts that we need to accept. Okay, these sp3 hybridized orbitals overlap head-on from sigma bonds. Okay, then we'll talk about pi bonds. Remember? Okay, side-on overlap, right? Okay, side-on overlap of what kind of orbitals? This one is nothing different. It's the same as before. What's the opposite of hybridized? Unhybridized, right? Okay, so unhybridized just means it didn't combine. It didn't participate in this, which I will show you a few examples later. But what are unhybridized orbitals? What are they called? Okay, they are just called p orbitals. Okay, so just take note of that from now on. Your normal p orbitals are this one that we learned back in chem bonding. These guys overlap sideways to form pi bonds. You can see that? Okay, so here are some facts. Once we understand how these orbitals overlap, then we can look at the shape of different types of carbons. Okay, right, so we have that. Right, okay, so let's take a look first. In this version of this hybridization here, I have 4 sp3 hybridized orbitals. Is that? Again, these orbitals, these hybridized orbitals, how do they overlap? Head-on to form what kind of bonds? To form sigma bonds, right? So if one carbon has 4 sp3 hybridized orbitals, then what kind of bonds it can form again? Sigma or pi? It can only form sigma bonds, right? But how many sigma bonds do you think it can form? 4, exactly. So that's what's going on over here. In this hybridized sp3 hybridization, I have 4 of them. So I can form up to 4 sigma bonds. Straightforward, right? Okay, because they undergo a head-on overlap. So what kind of carbon does it okay, what kind of carbon has 4 sigma bonds? What shape of carbon? How do you arrange the 4 bonds on carbon like that? How do you have 4 sigma bonds? Are there any double bonds? No, right? Double bonds must have pi. But in this case, if it's all sigma bonds, it's basically all 4 single bonds, correct? In other words, this is a what shape? Tetrahedral, good. And tetrahedral carbons from now on, you should recognize it as sp3 hybridized carbons. So that's what they can ask in the exam. They give you a carbon. If you recognize that it's tetrahedral in shape, then you must tell me that it is sp3 hybridized. Does that make sense? Okay, so how do we get until here? Let's just repeat what we just did. I combine 1s and 3p to form sp3. 4 of them. 4 sp3 can only form 4 sigma bonds, and the only way you can form 4 sigma bonds on carbon is a tetrahedral shape. So that's only one shape of carbon that we've gone through. We still have another 2 more shapes we'll talk about. But pretty much, this is just an extension to pretty much chem bonding. Chem bonding, we talk about orbital overlaps. This is an extension of it. Okay, so this is not obviously the only shape of carbon that you see, right? Are there any other carbon shapes you can think of? Other than tetrahedral? Okay, so it's in the notes as well. Okay, but then you should recognize these 3 shapes for carbon. Another one will be trigonal planar. And let's just discuss what is the hybridization of a trigonal planar carbon. Just now, tetrahedral is sp3, right? Now we don't know what it is yet. Never mind. Okay, so first of all, right, we can actually work things out. Just now we mentioned that tetrahedral has 4 sigma bonds, and hence it has 4 sp3 hybridized orbitals. Makes sense, right? Okay, so I remove this. Okay, over here, then, how many sigma bonds and how many pi bonds are there? Perhaps we can use that, right, okay, to discuss the hybridization. 2 sigma, is there only? Okay, there's 3 sigma and 1 pi. Okay, so let's take a look at how this works. If there are 3 sigma bonds, means what? Okay, there will be 3. Now, we do not know what a hybridization is, and it will not be sp3 because different types of carbons will have different types of hybridization. sp1, I have no idea, never mind yet. How about pi bonds? If I only have 1 pi bond on a trigonal planar carbon, that means I only have 1 what? How do pi bonds form? Side-on overlap of your normal p orbitals, right? So that means I only have 1 p orbital. Can see that? Now, if you see this, unhybridized just means it's nothing special. It's just a normal p orbital. So I want you to take a look at this diagram again. And what we're going to do here is I'm going to draw another version of this hybridization. I'm going to space to draw it again. So I want you to come from here, right? And then let's just hybridize it one more time. Now, yet again, can you see that I have 3 p orbitals here? But do I participate all of them in the hybridization? Okay, I shouldn't, because as you can see here, I have one p orbital that I must have, right, in order to form that one pi bond. Okay, so you follow me here first. I have one p orbital that must be reserved. You must choke him first. So he cannot go and combine. Make sense? So in other words, one p orbital cannot participate in this process. So he's just going to be normal. His energy level is going to be the same as before. So I'm going to take out one p orbital in advance because I know I need to form one pi bond. Does that make sense? So with one p orbital out of the way, the rest will undergo hybridization, right? So how many is this? One s orbital combines with two p orbitals. So let's combine them. Now they are in the level that's in between. 1s combined with only 2p. So what will they become? Make a guess. 1s 3p becomes sp3. 1s 2p becomes sp2. Exactly. So how many sp2 hybridized orbitals do I have? 3. And can you see this makes sense? Having 3 sp2 hybridized orbitals allows me to form 3 sigma bonds. And that's why I have 3 sigma bonds in the trigonoplanar. And that one pi bond comes from the one p orbital that did not hybridize. So in other words, look at these numbers here. It corresponds to our diagram. Okay, again, the electrons are arranged like this. 4 unpaired electrons allows us to form 4 bonds. So in other words, why I say hybridization is an extension to chem bonding is because we have learned sigma and pi bonds before, we have learned their orbital overlaps before, and we have learned their shapes before. With all these shapes and all these types of bonds in place, we can pretty much understand this relatively easily. Okay, it's not that difficult. So from now on, let's just accept this fact. Tetrahedral carbons is sp3 hybridized. Trigonoplanar carbons is sp2. Okay, good. So yeah, we are just discussing carbons. Do have nitrogen, do have oxygen. That will maybe late into J2 more advanced topics, then we cover that. But for now, you just need to recognize the shapes. Okay, and carbon only got 3 shapes. Yeah, I know VSEER theory, the shapes, right? A lot of people can't really remember. Okay, but we start here. Okay, only got 3 shapes to discuss. So far, so good. Okay, and okay, so I kind of run out of space on the board already, so I would have to delete maybe one of them. Okay, let me keep the S here now, okay, because we've seen that enough. Let's just use this space for another hybridization. Okay, so there's only one more shape to go through. Okay, so just copy whatever you need to first. Any questions, just clarify up. I'll move on to the last. So just a quick question, right? Okay, how come we are only discussing between 2s and 2p? You may be arguing, right, that hey, electrons are always moving. So why not the 1s electron also participate in the hybridization? Why don't have? How come the 1s never participate in anything? Any guesses? Sorry? The what? It's pair already, but this one pair already also. Right? But these guys participate in the hybridization. They exist as one family. But what is that? This one, right, just doesn't participate in that. It's too low. Exactly. We already identified this just now, right? The energy gap between 1s and 2s is so large to the point where the electrons just cannot jump on top. E1, 2 also cannot. Too high already. So we ignore 1s over here. We're only looking at the second quantum shell. Okay, so that's what we have so far. And I'm just going to show the final hybridization. Is there another way you can arrange carbon? I can have 4 sigma bonds, I can have 3 sigma and 1 pi. Is there another shape that you know? Single bonds, double bond, finally, triple bond. Okay, so I can have a triple bond like this and then a single bond, right? What shape is this? Linear, good. Okay, so having a linear shape, right? Again, what hybridization is this? You might be able to guess, but let's just see how this works. Okay, but first of all, let's just identify the same stuff. How many sigma? How many pi? Okay, good. 2 sigma and 2 pi. Okay, remember, a triple bond is made out of 1 sigma and 2 pi. So this is 2 sigma and 2 pi. Okay, so now we have a linear shaped carbon. Let's look at our breakdown first. Linear is made out of 2 sigma and 2 pi, right? Now, we do know that if you want to form two pi bond speeds, you need to have what? Yes, you need to have two p orbitals that do not hybridize. He cannot participate in this activity here. So what I'm going to do first, I'm going to take out these two p orbitals, and then their energy level must be the one. The same. Good. The energy level must be the same as before. So let me just list out the two p orbitals here. And instead, with these two p orbitals out of the way, then what is the hybridization now? 1s mixed with 1p. So if you have 1s mixing with 1p, what do I have? They hybridize into sp. Okay, there's no 1, it's just sp. So these are called sp hybridized orbitals. Again, we have 4 unpaired electrons arranged like this. So let's just count now. How many? Okay, if I have 2 sigma bonds, I will have what? 2 sp hybridized orbitals. Make sense? 2 sigma, 2 pi, so 2 sp and 2 sp. So these numbers over here are especially important. Later you'll see why as well. You don't need to memorize these numbers because you can definitely find out what's the sigma and pi on the spot. You know how many sigma, how many pi, and as long as you remember what kind of overlaps is with what kind of orbitals, you'll definitely find the number of all these orbitals on the spot. Can see that? So we're working all this out. So we know that whenever you see a near carbon, it must be sp hybridized. Okay, so that's how the diagram works as well. The diagram has been tested, not very often, but it has come out recently. So it is good to draw in all these diagrams as well. You have to draw 3 of these diagrams, 3 separate hybridizations, and go with it as well. Okay, but that's basically hybridization in a nutshell. Okay, we have some other stuff to do in the notes. Okay, so after we complete everything, now we can go look at the notes. Okay, as you're writing, okay, let me just quickly summarize. Okay, we have 3 types of hybridizations, and each one corresponds to a K. How do you know how many hybridized and unhybridized orbitals there are? You just need to count the number of sigma and pi. Just remember sigma, K long overlap of hybridized orbitals. Pi is only p orbitals. Done. So hybridization is quite a small segment, right, in the grand scheme of things. Okay, but then I need to spend some time, right, making sure everyone understands this. Yeah, okay, so that's that. Okay, once this is done, I will raise a few things. Okay, and right, okay, so we have completed our first part. Okay, we have looked at the concept, the background between of hybridization. Now we're going to look at drawing. Okay, we're going to draw what? Orbital overlaps. A lot of the times, right? Okay, the first part, just now, they can always ask you guys this simple question. What's the hybridization of this carbon? You just need to write sp2, you get 1 mark already. Okay, that's for the first part. Now let's look at the second part. Right? They can also test you guys how to draw orbital overlaps. Now we don't hit on overlap, we just going to draw like a Venn diagram and all that, right? Okay, but that one's not as simple here already. Because from now on, you must teach the idea of S and P orbitals separately. Now our carbons is hybridized orbitals and unhybridized orbitals. So no more just S overlapping S. So we have to now change up, right, our orbital overlap diagrams as well. So let's take a look at a few. Okay, so now we can look at the notes, and I need you to look at that first page, page 32, if I'm not wrong. Yeah. Okay, on page 32, we will first look at sp3 hybridization. Let's look at the first box at the top. Draw the hybridized orbitals. Now, how does a hybridized orbital look like? Okay, so let's do a quick recap. How does an s orbital look like? Any idea? Yeah, it is. How do you describe it? Is it circle? Okay, it's not circle, it is spherical. Okay, S for spherical. Okay, because you cannot write circle because circle means it's 2D, but in fact, life is 3D, right? Okay, so the must tell me it's a spherical. Okay, then how does a p orbital look like? Okay, dumbbell, good. Okay, it looks like a 8. Okay, basically, when we hybridize these orbitals, S hybridized with P, let me just show you something first. When they combine together, this is how the orbital is going to look like. It's like a P orbital, but one side is inflated, the other side is like not. Okay, don't ask me why it looks like this, just looks like this. Okay, and the thing is, all the sp3, sp2, and sp, right? all of them look like this. But what differentiates them apart, right, is how you arrange these orbitals. So let's look at the first one. We are talking about sp3 hybridization, so focus on this part here. Okay, how many sp3 hybridized orbitals are there? 4, as we mentioned here. Okay, and how do you arrange 4 of these guys? It has to be arranged in obviously the tetrahedral shape. So just take a look at this first. Okay, you have to draw these in a tetrahedral formation. 1, 2, 3, 4. Makes sense, right? Okay, it looks very similar to this. And then, okay, because one side is inflated, the other side is not inflated, right? We need to add that in as well. So there's the small parts. Okay, just add that at the other end of the parts. Okay, so it looks something like this. Okay, so this is something that you may be asked to draw. These are 4 sp3 hybridized orbitals arranged in the tetrahedral shape. Okay, yeah, so give it a try. Okay, try to draw this. Like what I did just now, you just have to draw the big parts first. Draw the big parts in the form of a tetrahedral shape. 1, 2, 3, and then 1 down here, 4. And then you just fill in at the ends, at every opposite side, you just fill in 1, 2, 3, 4 small little gaps like this. Okay, so this one requires a bit of practice now. Okay, but then when you first draw this, it will be quite hard. You also do it. Eventually, we will know how to draw. Right. Okay, then just label that 4 sp3 hybridized orbitals. Okay. Okay. Yes. Okay, what we're going to look at next is the box at the very bottom. Okay, so to discuss sp3 hybridization, sometimes, right, this is just asking you to show the orbitals. But what if the question says show the orbital overlap? Okay, when they ask for orbital overlap, you must really show the orbitals overlapping. I never show it here, right? So look at the box at the bottom. First of all, let's draw for a sample compound. Okay, we're going to draw for ethane. Okay, as we mentioned, ethane has, well, 2 carbons. And it is an alkane molecule. As you can see, the carbons here are tetrahedral sp3 hybridized, right? Okay, so we're going to use this to draw our orbital overlap. Let's try out. Okay, first of all, let's look at the carbons in the middle. The carbon in the middle, okay, let's just draw 2 carbons like this, leave a bit of space in between. And first of all, I need to show how this bond is formed. This is what bond? Sigma. And how does this sigma bond form? Head-on overlap of SP. Okay, correct. Okay, so this is how you describe the sigma bond in the middle here is formed by the head-on overlap of sp3 hybridized orbitals. Make sense? So let's draw the one in the middle first. Draw a sp3 hybridized orbital here as well, and we just need to shape this portion, call it the sigma bond. Again, now we need to label our hybridization also. So label these as sp3 hybridized orbitals. Now, I know, right, okay, there's another side which is much smaller like this. Okay, but when you draw the orbital overlaps, you can ignore the smaller part if you show the atoms. So we don't have to show the small part over here. Okay, so just follow me first. One carbon over here, does it just have that one sp3 hybridized orbital? No, right? It has how many others? Another 3 more, right? Okay, so we have 1, 2, 3, 4. All of them are the same. Okay, so what do we need to do here? Okay, just have to draw the same thing, but for a tetrahedral shape. Okay, so take a look. I just have to draw one up here. Here. Can you see it just looks like a tetrahedral shape also? Okay, so all these are also your sp3 hybridized orbitals. Let's just draw them all over here. Okay, so you're just drawing basically this diagram, but instead of just lines, you're showing me how the lines are formed because of orbitals overlapping. Okay, but let's just go a little bit further here. You can see that the carbon forms a bond with H, right? A sigma bond must show the orbital overlaps. Currently, I don't see any overlaps, correct? So I have to draw a H atom. What is the orbital of a hydrogen atom? Okay, it's just one S1, right? So it's just a S orbital. And the S orbital looks like a spherical shape, right? So remember, if there's hydrogen, you cannot use P because it just doesn't have a P orbital. So very simply, right, okay, let's just draw a sphere like that. Overlapping this you can call it your H atom. Just label this as your sigma bond. You just have to repeat this, right, for the other 3 as well, because since they are all the same thing. Okay, take a sphere, overlap, label sigma. Last one, same. Now the thing is, usually in exam, they are only interested in the carbon in the middle. Okay, so you don't actually need to draw like pictures. But for our own understanding, just know all these are head-on overlaps. In fact, there's no pi bond here, so there should not be any side-on overlaps at all. Okay, so repeat the same thing for the other side. Okay, so I'm just going to draw again another three more, and they look like a tetrahedral shape, right? Okay, so sp3, sp3, sp3. Okay, all these hydrogen with their s orbitals, sigma bonds. You just need to repeat the same thing over and over again. Okay, so this is how you draw orbital overlaps, right? For each orbit. Okay, give this a try, right? Remember to label as well. Okay, they will always ask you guys to draw a label diagram. So it's quite important. Okay. Right. So as you can see, the two diagrams that we've drawn on this page, the first diagram is if they ask you to just draw the orbitals. But the second diagram is if they ask you to draw for orbital overlaps, then two different things. Okay. Nice. Okay, so with that said, right, we can move on to the next hybridization. Okay, we're just gonna like check things off on this. SP3 is done. Next is SP. Okay, so let's take a look. Okay, so for SP2, I have three SP2 hybridized orbitals and one p orbital. Again, all these numbers is because you count the number of sigma and pi bonds. Okay, so let's first draw the orbitals. No orbital overlaps yet. First of all, how do you draw SP2 hybridized orbitals? Again, each one of them are the same. It's the same shape, but it's just arranged in a what formation? Trigonal planar. Good. Okay, so this tetrahedral formation. Now you just do the same thing again. Just draw the big parts. The big part, big part, big part. So it's like a little fan blade, right? And then afterwards, just fill in the small parts on every side of the center. Okay. Then from there, you can label this as three sp2 hybridized orbitals. See that? So the difference is not in the shape. The shape is all the same one. It's just that their arrangement is different and the number is different. Okay, but apart from that, what else is there? Yes, okay, so let's draw the p orbital separately also. Okay, again, the p orbital, right? There's no one small, one big. It's just the dumbbell shape. So this is your one p orbital that is unhybridized. It didn't undergo this process. Okay, so that's that. Okay, let me try to draw the orbital overlaps now. When it comes to orbital overlaps, first of all, let's draw in the molecule. We're going to draw for EE molecule. So you can already see the difference. Okay, the carbon here is trigonal planar. So the carbons here are both sp2 hybridized. But now there's a double bond in the middle. And again, always settle the middle. The middle here has what bonds? Okay, one pi and one sigma. Okay, so let's settle them separately first. Okay, I first draw my, okay, let's use this now. Okay, draw the two carbons in the middle. And let's do sigma first. Okay, how do you draw sigma bonds? K on overlap of sp2. Good. Okay, so now we are looking at the sp2 hybridized carbons. Okay, so draw two sp2 hybridized orbitals, one each. Label, and then of course shape, and right there your sigma bond. Okay. Okay, so that's sigma done. Okay, but let's settle the pi bond as well. How do you form a pi bond? Okay, sideway overlap of the normal p orbitals, right? Okay, so let's draw the p orbital with a different color. Okay, if you have a different color pen, I recommend that as well, because that's especially necessary for final hybridization later. Okay, but yes, okay, we have the two p orbitals like that. Now remember, for p orbitals, you need to overlap both top and bottom, and then you just label one of them as pi. Do not label bottom pi and top pi and so on, so it doesn't make sense. Okay, this is just one pi bond, so it should be top and bottom both overlap to form this pi bond. Make sense? Okay, then from there you can just label your p like this. So we have now settled my one sp2 and one p. We still need to settle another two more sp2s. Can you see where the two sp2s are used for? Okay, you look at this diagram over here. Around one carbon, is it just a double bond? No, right? Okay, there's still these two bonds over here. What are these bonds? They're both normal sigma bonds, right? So what orbitals must you draw here? Yes, good. Okay, sp2. And again, let's show the trigonal planar shape. So it looks something like this. Okay, and then from there, just go and label your sp2 hybridized. Okay, as you can see here, the numbers must correspond for each carbon. If the carbon is sp2 hybridized, you must have 3 sp2, 1p. And that's exactly what I have here. 3 sp2, 1p. Okay, repeat the same thing for the other side. And normally, this is enough for your whole diagram already. Okay, you will notice that I ignored all the hydrogens and the N's because most of the time the question don't ask for the whole molecule. The question just asks for the carbon in the middle. So you can actually ignore the rest, like all the hydrogen atoms and whatnot. Okay, so hydrogen normally can ignore one. So just draw everything on two carbons. Okay? Yeah, okay, so just spend some time drawing that, and then we can move on to the next. Right. Right. Okay, let's look at our final hybridization. This one, the diagram might look a bit messy, so it's good to use different colors. Okay, but first things, let's look at the final hybridization. SP. Let's label let's draw the orbitals first. Don't draw the overlaps yet. Okay, so how many were there? Okay, good. Okay, so we're going to draw for this molecule here. As you can see from each carbon here, so sp hybridized, 2 sigma and 2 pi. So we have 2 sp and 2 p. Good. Okay, how do you draw the sp orbitals? How do you think they are shown? Okay, it is a linear shape, right? So it just flat 180 degrees. It's not very easy to draw because the technique is very simple. Draw a big infinity sign, and then in the middle, draw a small infinity sign. So you can see, right, it's basically just two of these orbitals arranging themselves in a linear shape. So this is the work of two sp hybridized orbitals. But at the same time, what else do I have? Yes, I have two p orbitals. Now again, they are separate. Do not overlap them or whatever. Okay, they are just standalone, unhybridized p orbitals. So you must draw this set over here. Let me just divide this so that it okay. Confused. Okay, so this is your linear shaped carbon. Okay. And this time round, we're going to draw the orbital overlaps one more time. Okay, let's just modify this. Again, let's focus on the carbon in the middle. It's held by a triple bond, right? So the triple bond is made up of what? 1 sigma and 2 pi. Okay, let's settle all this first. 1 sigma, 2 pi, and then on the other end, there's another sigma, right? Okay, let's just settle the sigma bonds first. How do the sigma bonds overlap? Head-on overlap of sp. Good. Okay, so I have two sp hybridized carbons like this. But now you must label them correctly. This is just sp. They can still form a sigma bond like this, correct? Now focus on just one carbon. There's also another sp hybridized orbital, right? Where is it? Sigma is sp, right? So it's on the opposite side. So you just need to draw another one, flat like this. Label it sp. As you can see, I have my carbon here that looks like a linear shape, which is what how they are arranged. Okay, so I've that done already. Let's settle the 2 pi. Let's settle 1 pi first at a time. So to form a pi bond, again, how is it done? Side-on overlap of p orbitals. Unhybridized p orbitals. I'm making you recite all this because they will always ask us. Okay, so look at one carbon here. Let's draw one p orbital in red. Okay, so again, they overlap sideways like this, form one pi bond. Okay, and let's just call these the p orbitals. Okay, I forgot for this side as well. Okay, let's just mirror this out. Carbon has one sp, another sp. Okay, linear shape. Okay? Okay, you can put your H's here as well, but we ignore the H's. Next, we have another pi bond to draw, right? Okay, how do you think we're going to draw this pi bond? Okay, the label, the top one? No. Okay, because that's not correct. Because as I mentioned just now, you must overlap both at the bottom and the top to have only one pi bond. So you can't just label the one at the top. Okay, so right, if you do that, another flaw is that I've only drawn one p orbital, right? How many p orbitals am I supposed to have? Two. Okay, I've only drawn one for one carbon, so that's not enough. I need to draw another p orbital. So I'm going to draw it in purple, but how do I draw this other p orbital? Can I just do this? Okay, two p orbitals then just overlap. Okay, I can't actually do this now. Okay, for a very simple reason, and it's also in the notes. So I need you to write it down or highlight it. Okay, you can't draw the two p orbitals parallel and beside each other because the two p orbitals must be perpendicular to one another. And that's for a very simple reason. It's because p orbitals are what types of p orbitals are there? Just now I mentioned. There are three types of p orbitals, right? Yeah, p, x, y, and z. Now, what does y, x, y, z mean? They're all in different planes, right? So x-axis and y-axis is perpendicular now, and with the z-axis also perpendicular. So the p orbitals cannot exist on the same plane now. If this is py, then it must exist another one on, like, let's say, pz. Okay, but you don't need to specify what now. So I'm going to draw like this. Okay, now it looks a bit weird. It looks like it's 45 degrees, right? But can you see it's actually 90 degrees apart? It's like the red one is like that, right? Then the other one is like this. It is like, because we are drawing on the 2D paper, so it's very difficult. Okay, but anyways, you just need to visualize this. This is like facing inwards. So it is 90 degrees apart. And this is how we show that. Okay, so again, I label my p orbitals, and you must both highlight top and bottom to call this just one pi bond. So now I have successfully drawn two pi bonds because each carbon has two p orbitals. We have to be separate. Does that make sense? Okay, so this one looks very messy. And this is one of the harder ones to draw. Okay, but they have tested before now. Okay, that's everything for this. If you find it a bit messy, right, I suggest just focus on one carbon and count all the different types of orbitals. I can see 2p and 2sp. So it corresponds to this is correct. Okay, okay, so that's our orbital drawing for linear shape. Okay, right. So we are done with the second part of this portion. We have drawn all the orbitals. Okay, now let's look at the third part, right? The third part is actually not that difficult. It's an application of hybridization. Okay, hybridization can allow us to explain bond length and bond strength. Okay, so how do we do that? Okay, but before that, there's one question on page 36. I think later that we do that. Okay, we look at page 37 first. Okay, let's discuss the application. Different types hybridization. We only have three types, right? SP3, SP2, and SP. These guys can help us explain why they have different bond lengths and strengths. Okay, so the very simple example, right? Let's just look through the most simple one. Okay, in the notes, you can also see the same thing. I have double bond, single bond, and triple bond, which is corresponding to what we went through just now. Okay, single bond is like this. Okay, double bond and then triple bond. What are their hybridizations? So that's what hybridization. Okay, then this. Okay, then this is SP. Okay, so you take a look first. We can actually explain bond length and bond strength. Now remember one very important idea. Bond length and bond strength is dependent on the effectiveness of, okay, close enough. Okay, it's dependent on the effectiveness of orbital overlap. Okay, very, very important keyword. Okay, it sounds cheap, right? That's not. Basically, if the orbitals overlap more, you think it's stronger or weaker? Stronger. You can't say overlap more, like, it just doesn't sound good. So that's why they say overlap more effectively. Now, if you overlap less, which is less effectively, strong or weak. See, the overlap very little, right? So how's that strong? Very terrible. Okay, so that's the same idea here. Just know, bond length and strength must use this keyword. Okay, so let's take a look. How do you explain for this? Okay, so we're going to look at how hybridization will help us with this. Okay, for this, we already mentioned just now that they are sp3, 2, and 1 hybridization. So look at the orbital overlaps here. The orbitals that are overlapping to form this is an sp3 hybridized orbital and another sp3 hybridized orbital, correct? Okay, same thing over here. This one will be sp2 and sp2. Final one is like what you see over here, sp overlapping with sp. Now, we have the link to the idea of effectiveness of orbital overlap. How do we do this? Okay, so this one, right, just take note, is dependent on a very unique thing that we have to look at, the percentage of S character. Now, you don't really need to know why exactly, okay, but what do I mean by percentage of S? It's just math. Okay, what do I mean by that? Okay, so take a look. What is just percentage? You see, out of all the alphabets here, how many of the alphabets are letter S? That's all we are doing. Okay, so how many alphabets are there? Yes, so there's 1, 2, 3, 4, 5, 6, 7, 8, right? Yeah, that's it. Okay, so we have 8 carbons, sorry, 8 alphabets. How many of it are S? 2. So 2 out of 8 is just 1/4, right? So we are safe to say that this is 25% S. This one, 1, 2, 3, 4, 5, 6. 6 alphabets, only 2 are S. So 2 out of 6 is 1/3, right? 1/3 is about 33% S. Finally, look at the one on the right hand side. This one is what? Okay, half. So 50% S. Now, as you can see over here, the percentage of S character is increasing, right? So we just need to understand this. When the S character increases, percentage of S character increases, getting of the explanation. A fact that you also need to accept is that the effectiveness becomes higher. Okay, the orbitals overlap more effectively. So that's just a thing that we need to accept in this portion. The higher the S character, the more effective the orbital overlap, which means what happens to the bond length? Shorter or longer? Shorter. You overlap more, you can clearly see visually that the bond is getting shorter. So bond length decreases, whereas bond strength will increase. The more you overlap, the more secure it is, so it's going to become stronger. This is the explanation for this segment. That's it. And that's the only application we're going to look at. We can look at some example questions also right after this. Okay, but one question you may be asking me is this. Is it possible to have multiple different types of orbital overlaps? If I have sp3, does it necessarily have to overlap with another sp3? From what we see over here, it looks like yes, right? But actually, no. Okay, let's look at a certain example. I can draw out this particular molecule. Okay, just take a look at how this molecule looks like first. Okay, and we shall see. Okay, let's take a look. You can draw in this example somewhere as well. This will help us prepare for the next question. But you see, I'm going to label this as carbon 1, carbon 2, carbon 3. Okay. Can you tell me what's the orbital overlap between carbon 1 and carbon 2? Okay, like this. sp3 overlapping with okay, you look at the carbon, look at what's around it. What's the shape of that carbon? What's the shape of this carbon? Let's try here. What's the shape of this carbon? Yeah, linear. Linear is what? So that's the answer. So it is possible, right? This particular bond over here is sp3, sp hybridized. Okay. So perhaps let's just expand on this molecule a little bit more. Okay, so let me draw in another one here. Okay, I'm going to label this carbon 4. Can you tell me what's the orbital overlap of C3 to C4? sp2, sp2? Not really. Look at what's sp. What's carbon 3? Carbon 3 is linear, so it's sp followed by sp2. Okay, trigonal so sp2. So you can see carbon 3 and 4, the orbital overlaps are different as well. So you must look at each carbon individually, look at its shape first. Then you can identify the orbital overlap. So now let's just discuss one more very interesting thing. Both of them are single bonds, right? You look at them, it's single bond, single bond. So they should, by right, have the same bond length and bond strength, right? But if you look at the orbital overlap more closely, you take a look at the orbital overlaps, are they the same? No, it's a different type of orbital overlap. So you can't just say, oh, look, single bond, perfect. They have the same bond length, same bond strength. No, that doesn't happen. Bond length and bond strength, you must look at how effective the orbitals overlap. And to determine that, you must first determine what are the orbitals in the first place. So can you just tell me which one has more effective orbital overlap? Okay, the bottom one, because the bottom one has what? There's a higher proportion of S, right? Okay, so the bottom one has a higher percentage of S character, hence it has more effective orbital overlap, and that's why it has what? The bond is shorter and higher, so it's stronger now. Shorter bonds are stronger. So let's just write down this sample example somewhere in the notes. Okay, so yes, they can mix and match different types of bonds. On first glance, they look like single bonds, but you must look at their hybridization. Okay, never will they be the same one. Different types of hybridization, the different percentage of S. Okay, and that will help us address the question on page 38 as well. Okay, so you can afterwards, okay, you can read the question on page 38. It is pretty much the same thing as this. Okay, then we can answer that. Okay, so once done copying, you can read that also. The answer for this? Yeah. Right? Yeah, B is the answer. Okay, I know the answer, right? The option doesn't seem to explain a lot of things. Okay, but this is what the question is saying. In an ethane molecule, this is the bond length. In an ethyl molecule, this is the bond length. But in particular, they are interested in this structure here. What's the relationship of this bond length with the other two structures? This bond length with the other two bond lengths. This one is in between. Okay, so again, they are all carbons, right? So we need to discuss using percentage of S character. Okay, so what's the hybridization of methane? What's the orbital overlap? sp3 overlapping with. Okay, so how about ethyne? sp. Okay, so how about this one here? In between C2 and C3, hybridization is sp and sp. Good. Okay, so with that said, we can determine the percentage of S. This one is about 25% S. This one is 50% S. And if you were to make a prediction, right, this one also has to be in between the other two, right, based on the data that we have been given. Okay, so you can already see that this is about 33% yes. Okay, so yes, good. Okay, 33% S, so it explains why the bond length is intermediate of the. Okay, so that's the answer for this one. Okay, there's only one more question that we skipped just now. Once we are done with this, we can move on to the next segment. Okay, so can you just take a look at page 36? Okay, page 36, they gave you the skeletal formula. Some of it is not skeletal, as you can see. Okay, then from there, right, okay, you need to determine how many sp, sp2, and sp3 hybridized carbons there are. Right? Now take note, the one at the end over here, right? Okay, they purposely draw CH2CN. I suggest you draw out all the bonds also, so you can see clearly what's the shape on the particular carbons. There are two carbons here, so just draw the shapes. Okay, then you wouldn't miss out on that. It's 7 to 10. Right? Oh, the glass water. Okay, we have to move to the other smaller class. Shit. Hey, yo, hello. What is here? Oh, oh yeah, your physics. I was stop it. Oh, then now your physics. Then, huh? So bad. Okay. Already. Oh, they're okay now. Right. So I know last year was very difficult. Oh. What? Then must move on, what? This kind of, you don't move on a bit, it makes sense. The hydrogens. What do you mean? Yes, for that one part of the molecule, you need to draw like it. So that you can see the bonds correctly. So it looks like this, right? We're talking about this one here, right? The rest you shouldn't draw the edges. If not, it will take too long to do this question. Because you can actually determine the shape, right, without even looking at the edges. Like, let's do maybe a few. Like the first one over here, right, is what? SP3. Okay, because it's only made out of single bond. Okay, so if you know this SP3, how about this one? It has a double bond onto it. So it has to be what hybridization? SP2. Okay, because double bond just means the carbon is trigonoplanar. So you just have to repeat the same process of this one is SP2, this one is. You only see single bonds. So it's that trihedral SP3, correct? Okay, but look at this carbon here before we go on to the rest. This carbon here has two natures, so we draw the two natures like this, right? And then to bond with the CN is what? Double, 1, 2, 3 already. So it's a single bond. Yes, if we see it in this one bond. It has to be a triple bond. Okay, as long as your carbon fulfills 4 bonds, okay, you can see. So this carbon here is what hybridization. Okay, 4 single bonds, tetrahedral sp3. How about this one? Yes, this is the only linear carbon because you can only see one triple bond in this entire model. Okay, then you just keep on going on. Okay, how about this sp3? sp3? Okay, sp3. It is other. sp12. All single bond, right? So it's 3. Is that it? Yes. Okay, you see a double bond is sp2 already. Is that it? Okay, good. All single bonds. Okay, this one is fluorine, right? So we don't count those. You only count carbons. Is there anything else that we have possibly missed out? Did we miss out anything? Or we done? Because I have missed out a few. Sorry. Any carbons that I failed to account for? Is that it? Yes, okay. All these are usually a lot of people forget that these are carbons as well. Those are hanging at the tail end are carbons also. Okay, so these are what? Hybridization. Yes, okay, these are sp3 as well. Okay, from there, right, you just need to consolidate everything and just get the answer. So that's the process here. This kind of questions is just to train your, it's just a practice exercise, okay, for you to go and eventually, right, when you look at a compound, you can very easily see what hybridization is because of all these exercises. Okay, these are very common MCQ questions also, where they just give you and then they ask you to count. And you just cannot forget to count all those at the ends over here. And they never draw any bonds. Recommended is to draw the bonds. So you need to modify the one at the top. Yeah, okay, so that's what we have for this portion. So the answer here, I think, is B or C, right? Yeah, B, correct. Is it 1, 3, and 8? This answer, yeah. Okay, any questions so far? So with that said, that's hybridization. Okay, the next lesson we'll look at the tutorial questions regarding this. For now, we're going to have to move on to the last segment of this note. Okay, so we're going to move on to this thing called isomerism. It's not very difficult. Okay, it's just bit content theory. Okay, so we try to finish this by today. Later on, we'll take a break. Yeah, okay, so we can still go on. Okay, so with the next 1 hour, just nice, we can finish this up. Okay, so first, let me introduce the idea of isomers, isomerism. Okay, the most fundamental thing is this. Isomers have the same, or perhaps let's just split it into types. Okay? An isomer is something, right, that has the same overall number of atoms, but they are just arranged differently. So we have already encountered a few, right, where we went through the naming convention of all these compounds. Like I can have 4 carbons in a straight line, right? Or I can just arrange like that and I form a branch, something like this. They both have the same total number of carbons and hydrogen atoms. It's just that the way they are arranged is different, and their relationship is called an isomer. Okay, so there's just variations of the same molecular formula. Okay, so let's go through this first. There are actually 2 types of isomers. We need to split them up. The first is called structural isomerism. Your notes may have written the word constitutional, but like screw that. Okay, your use of structure is even better. Constitutional too long already. Yeah, okay, need spell. Okay, but what's a structural isomer? First of all, let's look at the definition. They must have the same molecular formula, like what I discussed, but different structural formula. Isomerism is something that you have actually touched on in secondary school. So pretty much, right, there's nothing new over here. Okay, different ways we can arrange an atom. Okay, so let's see how this works. We have actually a few types of structural isomerism. You can see the flow chart over there, right? The very nice flow chart. Okay, let's just discuss that. Now, the first one is called chain isomerism, and you can pretty much guess, right, what this is really. Okay, chain isomerism is between what and what? Any idea what's chain isomerism? Straight chain and what's the opposite of that? Like just now I draw already, right? Okay, there's a straight chain isomer, which is just your carbon atoms in a straight line, okay, which is something like this. Okay, so we call it a straight chain. Okay, the other one, which is what we did just now here, it's called a branch isomer. Okay, so branch isomer is something that obviously is branches. Okay, right. Okay, then let's look at the next one. Next one is called positional isomerism. So just take note. Position of what? It is the position of the functional group that is different. So for example, we have like alkenes. Alkenes, I can place the double bond on the first position there. Is there somewhere else I can place this double bond as well? I can also place it in the middle here. Any other variations? Can I place the double bond at the end? Is there another isomer? It's the same as the first one. Okay, good. Okay, so that's like an idea. See whether you can see the different types of isomers. Okay, and finally, right, the last one is functional group isomerism. Now, this one you wouldn't see very early. You will see this more in the later parts of organic chem. Okay, basically, they have completely different functional groups, but it still fulfills the same molecular form. Let me give you an example. Okay, right now, that example doesn't seem very familiar. Okay, there's a functional group we're going to learn eventually. It's called aldehyde. And aldehyde and its functional group isomer is called tone. Sounds very weird. Again, you don't need to know this now. And aldehyde looks like this. Okay, so what I'm saying is this. The functional group of an aldehyde is C double bond O with a H bonded to it. Okay, but for a ketone, it's a bit different. Okay, I will have just double bond O like that, no H. But you can see overall the molecular formula is the same one. Okay, I have 3 carbons here, right? So this is C3. I have 1, 2, 3, 4, 5, 6 hydrogens and 1 oxygen. You can see that. And if you do the same thing for this guy, this functional group, 1, 2, 3, 4, 5, 6 hydrogens, 3 carbons, and 1 oxygen. So they will share the same molecular formula. Okay, it's just that their functional group completely different reactions. Okay, different types of chemical reactions also. You can see that. Okay, no? So with that said, that's just one example. There are others as well, which I'm not going to go over now. But a lot of people get confused between these two. Positional isomerism is the same functional group but different position. You see that? This one is different functional group but same overall molecular formula. Right, okay, so this one's not really the important part. The important part that we're going to go over today is this over here. We call this second type stereoisomerism. Now this one is where you need to study. The rest, this one obviously not that important. What is stereoisomers? Okay, so you can turn over to page okay, that is on page 43. Okay, first of all, I think we do the question on page 42 first. We talk a bit about isomers. Okay, so they want us to draw all the isomers, right, for C3H6Br2. Now, there is a way to list down all the formulas. So we're going to teach you guys some techniques. Okay, but when you draw isomers like this, okay, let's go over how this works first. Okay, You don't know how many isomers to draw, right? Because they can ask you to draw all. What does all mean? Are you going to draw 5? Are you going to draw 10? Then if you draw 3 only, you ask yourself, is that enough? You tend to doubt yourself. Okay, so first of all, I want you to always take note. When you see a molecular formula, you must look at the carbon skeleton first. That's the most important part. I have 3 carbons, right? So you must draw a 3 carbon skeleton. Can you try that? How do I draw a 3 carbon skeleton? Okay, yes, exactly. Okay, it's just like that. Okay, but now, right, we just need to fit in a few more things. Skeleton, I don't have to draw the H. I just need to draw the BR. How do I fit the 2 BRs? Anywhere. What should I do? Okay, where will you want to put it? Up to you. You want to put one in the middle and you want to put another one in the middle? Or where's the second one? Where do you want to put the second one? You put in the middle. You can put one at the end. Yes. Okay, so this is one possible structure already. Usually the first structure you can just anyhow whack one out, right? Okay, and then you will see that it's quite possible. Okay. Okay, what's another structure that I can draw? Again, I can draw 3 carbons like that first. But what's another possibility? 2 at the end. Yes, okay, good. I can place 2 at the end. You can clearly see these are 2 unique molecules, 2 unique isomers. Okay, draw the carbon skeleton again. Where else can I do this? Okay, one on each side. Yes, exactly. Any more? Yes, good. Okay, then that's our answer already. So they did say all the non-cyclic structures. So you cannot draw any triangles or whatnot. Okay, it has to stick with this. So these are the only 4 possibilities. As you can see, having 3 carbons, the amount of possibilities are not much. But if they expand the number of carbons, right, it gets harder. If they increase it to 4 carbons, you're really probably going to have another 2 more isomers. So that's why they tend to give smaller structures. Okay? So that's just the basic isomerism. From there, then we'll move on to stereoisomerism, which is what we are basically going to focus on for today. Okay. Yes. Okay, so let's look at stereoisomerism now. Okay, so it's different from structural isomerism because the definition itself, you can see, is quite weird. Okay, for structural isomers, same total atoms, but arranged differently. But for stereoisomerism, they both have the same molecular and structural formula. Then you'll be like, what? How is that possible? Then how is that isomer? If they are both the same, wouldn't that mean it's the same thing? Right? But it's not, okay, because what they're different is, this part here. They have different spatial arrangement of atoms. What is spatial arrangement? I know now it just doesn't seem like anything legit, right? Spatial arrangement just means they can arrange on different planes. So it could be on a, okay, we'll look at some examples. Okay, but there are 2 types of stereoisomers. Okay, that we're going to go through. The first type is called cis-trans isomerism. Now, this is not very difficult, okay, but there are a few things to talk about. Under cis-trans, you must first look at the definition. There are 2 criteria that you need to write in the exam also. Okay, so first of all, the first criteria is that you need a covalent bond with restricted rotation. Now, what does it mean when a bond has restricted rotation? I'm just going to give you one example. You can take note also. A double bond. A double bond cannot be rotated. Any idea why? To make a guess. Sorry? Okay. Okay. So single bonds you can actually rotate okay, but for double bonds you can't actually twist it. Yeah, I know rotate doesn't look real now, but it's because double bonds are too strong. Okay, they are way stronger than single bonds, so you can't rotate. Let me just give you an example. If I have a single bond like this, I have a Cl here, I have a Br over here. I can just rotate this around, right, such that now it looks like this. So imagine this, I pivot the left-hand side, then it's like when you squeeze a cloth like that, you twist the other side, right? Okay, it's the same thing. I hold this part, then I squeeze this. So then now it turns upside down, right? So this can be rotated because single bonds can rotate. But what does it mean when the double bond has restricted rotation? So if this was a double bond in the middle instead, you hold this part, can you turn? No, cannot. Okay, it will be locked into place. So it's essentially what is happening here is that when I have a double bond now, I cannot twist it until it's upside down here. If it's not possible to twist, are they the same structure? No, they are completely different structures. That's good. Okay, whereas for just now, single bond, are these the same or the different structures? They are the same because you can actually just rotate this to obtain this structure. But for double bond, since it's unique, if you're facing the top, means you're confirmed facing the top. If you're facing the bottom, means it's a completely new product facing the bottom. So that's what we mean by restricted rotation. Okay, so we have a double bond right that can do this, such that we can have two different isomers. If not, you end up with the same thing, right? That's not considered an isomer already. You can see the logic behind that, right? Yeah. Okay. But that's only one criteria. The second criteria, right, is that they have to be different groups bonded to each carbon on the double bond. So the double bond is made up of two carbons, right? Each carbon must have different groups. So what does that mean? Okay, let's look at a few examples. I'm sure you can tell already, cis trans is mainly for double bonded structures. Okay, so we're going to focus on aldehydes, which are double bonds. Okay, so what do I mean by different groups? Okay, look at the carbon on the left, right? Okay, so if this guy is an H, this guy is a CH3, is this different group? It's different group, right? Obviously. So the carbon on the right, if this is H, this is CH3, is this different group? Okay, it's different also. Now, the misconception is a lot of us will think HCH3 is the same as the left one, right? But no, we are saying it's on each carbon, then you have different groups. So you don't look at them together. Okay, you cover the right, you see, are they different? If answer is yes, you can move on already. You cover the left now. Are they different? Answer is yes. So this structure here fulfills both criteria, and hence this guy can undergo cis-trans isomerism. Okay? So let's look at this. What is cis and what is trans? So they are just Latin. Okay, cis just means, okay, you know what transgender is, right? Transgender means you are the opposite gender, right? Okay, so you're born as a one gender, you accept the opposite. So trans just means opposite sides in this context. Okay, opposite side of the double bond. You will see what that means. Then what do you think cis is? Okay, cis means like cisgender, which is like us. Right? Okay, so you have the same gender as what you are assigned at birth. It's the same idea here. Okay, same sides of the double bond. So you take a look. Currently, right now, what are we looking at? What is same side? What is the different sides? Okay, general rule of thumb is this. You find the hydrogen atoms. So the hydrogen atoms currently, are they on the same side or opposite sides of the double bond? Okay, same sides. Okay, so you see the double bond is horizontal like this, right? You can imagine the double bond as a river. A river is flowing from the left to the right. But can you see, imagine you are this guy, and then there's someone else also over there, right? They are on the same side of the river bank. Can see that? Okay, so we're not saying this way. Don't go and cut the double bond this way and say that the H's are opposite sides. So okay, it is flowing this way. That's where the double bond is. Okay, so this is considered a what molecule? Yes, okay, so this is the cis isomer. Now let's draw the trans isomer. What do you think the trans isomer should look like? How can I modify this such that it's a trans isomer? The hydrogen atoms are on opposite sides of the double bond. You can see that. Okay, the river is like this, horizontal, and you're on opposite sides. So what I've just done over here, okay, you take a look first. This is the trans isomer because the H's are on opposite sides. Now, did I just twist this such that I can get this structure? Did I just twist it? Can the double bond be twisted? No. Okay, so this is a completely new structure. You cannot twist the first structure to get the second one. So it's completely different. That's why one's called cis, one's called trans. Does that make sense? Yeah, so that's what cis trans looks like. Okay, and that's like the basics. Okay, okay, so with that said, we have pretty much covered the whole of page 43. Page 44, we have a few examples of this and that also. Okay, so let's see. These are correct examples. What is a wrong example? Now, it's when they do not have different groups. What does that mean? Okay. So let me give you a structure over here. Okay, can this guy undergo cis-trans isomerism? Yes or no? Okay, so why no? Okay, the carbon on the left, does it have different groups? Yes, okay, so the carbon on the left is good, but the carbon on the right is the same, right? Instantly out. Okay, that's one example. There are some other examples in the notes that you can go and take a look. Okay, so we have to practice seeing this. The more structures we see, the more exercises we do, that will be quite obvious. Okay, now you will take a look at page 45. We're going to look at different types of alkenes, different types of structures that can also undergo cis-trans isomerism. Now, this example here is a cyclic structure, a ring structure, but with an alkene in the middle. Now, let's just discuss and see whether this guy can exhibit cis-trans. First, does it have a covalent bond with restricted rotation? Have double bond, perfect. Now, on this double bond, now I have these two carbons here, right? We have to check these two carbons whether they got different groups. Does this guy have different groups? Sure. There's something invisible, right? What is it? Okay, there's H's invisible, right? So this carbon, are these two different groups? Yes. How about this one? Also different. Okay, so perfect. It fulfills both criteria, right? But this is not possible. Okay, so take a look. Cycloalkenes cannot undergo cis-trans isomerism despite fulfilling both criteria. And let's look at the reason why. The reason is because of this thing called ring strain. Okay, forming rings is actually very strenuous, right, on the electrons inside. Okay, and why is that so? Okay, the ring is too small to accommodate the trans isomer. Okay, currently, right, is this the cis or the trans version? Okay, good. The H's are on the same side of the double bond, right? So this is safe. But the thing is, imagine how do you form the trans isomer? Can you see it's because like this part is the opposite? But when you turn this part opposite, can you see you're also breaking apart the ring? So it's very, you can't form it. So the thing is this, only rings with 8 or more carbons, which is not how you write it, with 8 or more carbons, then can form cis-trans isomers. But you'll never see rings that are 8 carbons, are too big. Most of the rings that you see is either 6 carbons or 5 carbons. So a 6 carbon ring is too small, so you cannot exhibit cis-trans. Your job over here is very simple. When you see a double bond in a ring, it doesn't undergo cis-trans. That's it. That's your job. Okay, nothing else. The reasoning, they probably don't ask. It's just for your own information. So as you can see, the example that I printed at the bottom of that page, the carbon has 8. Okay, the ring has 8 carbons. And it's possible to form the trans isomer because it's big enough. Okay, but this one too small already. You cannot do that. Okay, you don't need to visualize that. Even I also have trouble visualizing how that is done. Very weird. Okay, so let's not talk about that. Okay, can? Okay, so that's cycloalkenes. Okay, turn over to page 46. We have another 2 more scenarios. Okay, in these 2 scenarios, okay, let's take a look first. I'm going to look at a ring that looks like that. Okay, look at this particular example. This is the only example you need to know for this segment here. Let's see whether this guy can undergo cis-trans isomerism. Does it have a covalent bond with restricted rotation? Okay, you will say no, because we said that covalent bond with restricted rotation is a double bond. But I can tell you that this is restricted. Why? Because on top of double bonds, I want you to add on, rings are considered restricted as well. Okay, why are rings restricted? Can you twist the ring? No, because the ring is like rigid, right? Okay, you can't twist it. So that's why rings are also considered restricted. So despite not having a double bond, that's why the definition, right? A lot of students write this. The first criteria, double bond with restricted rotation. But that's wrong. Because if you write double bond, you're also discounting the fact that rings are restricted as well. But then now that's the tricky part. How on earth does this thing undergo cis-trans isomerism? There's no H's, right? There's no same side or opposite sides, right? So how should we do this? Actually, go and look at the H's again. Actually have one. Can you see these 2 BRs? I have H's on them as well. But currently it looks like they're on the same side. So what on earth does it mean by same sides and opposite sides in this case? Okay, so let's look at the answer here. Okay, this is quite special also. Okay, focus on the H. Okay, because we have this thing called stereochemical formula. I don't we haven't gone through yet. Later we'll talk about it. But have you seen the tetrahedral shape in your school's notes? They will use these bonds to show. What does the solid black color bond mean? Okay, just a thing. Tetrahedral, by the way, you must know, it is a three-dimensional shape. In other words, it is not a planar shape. So if you place tetrahedral on a flat piece of paper, there will be things protruding outwards and inwards. It's not flat now. Okay, so that's why they actually use this to show. Later I'll talk about this more. But this solid, I want you to imagine this bond is facing you right now. It's protruding out of the white. But then this dash bond is actually going inwards. Yeah, it's actually not flat on the board, it's inwards. These two, yes, they are flat on the board. This one is protruding outwards, this one is protruding inwards. Can you see that? Yeah, okay, so that's basically the idea of this. And because these carbons are both tetrahedral, right, we can actually now discuss this formation instead. Okay, you see just now here, double bonds, right? They are planar, right? Trigonoplanar. So this is completely flat. So we just look at same side and opposite sides. But now when we talk about same sides and opposite sides, I want you to look at this. Okay? Focus on where the hydrogens are. If I were to draw a cis isomer, how do you think this will look like? I'm not going to give you the answer. Think about this. Same sides, right? So the hydrogens, how should we draw the hydrogens? Yeah, I'm going to draw these bonds. Okay, you see these two are the normal bonds, right? So that means my bromine and H, I need to change it into the solid and dash bonds. Okay? Special bonds. Yeah, say again. You see the carbon here. Two of these belong to the ring, and it's basically just the normal bonds. That means the other two bonds must be with this kind of relation. So for cis, what I'm going to do is this. The bromine is going to be a solid bond, so the hydrogen is going to be a what? A dash bond. And because it's cis, that means the opposite side must be the same as well. So the bromine must be solid, and then H is also dash. So why is this a cis isomer? It's because the H's are both facing inwards, which is the same. Now, think about that. How do we draw a trans isomer now? I draw the same ring, normal. It's just a small little group here that I need to change into the tree. So if on top over here, I put the Br as solid, H is dash, right? Then the bottom should be out. Okay, sorry. Swap, yes, I heard you say swap, right? Yes, okay, because trans means opposite. So if the Br is facing outwards, now the Br must be facing inwards. And then the H now must be facing outwards. So it's because these carbons here, let me highlight the carbons in red. These carbons are tetrahedral, they are 3D, so you can actually change the plane of the smaller atoms. But for these, all these are planar, so I can only do same side and opposite sides. But this is same plane and opposite plane, so I want you to write down same plane. Look at the H's, both facing inwards. Trans means opposite planes. As you can see, H facing inwards, H facing outwards. You want to look at the PR also can. Okay, but this is a very important portion because they have tested this before. There's also one question in our paper. Yeah, but that's the main idea behind this. Can you understand this? Yeah. Okay, so I know a bit more challenging. Okay, so I'll go through a bit slowly. Okay, just as you're copying a summary, right? Tetrahedral carbons, you can change the planes of the atoms by giving me these funny looking bonds. Okay, so this one is actually not the complete version. You must draw the solid and dash bonds. Okay, they call it wedges in some notes. I call it solid and dash. I think it's easier. All good so far? Yeah, okay, so that's another way how cis and trans works. Now we look at the final one. The final one is very simple. Okay, the final example is this. Okay, so we've gone through cis, we've gone through trans. Okay, so I'm going to look at this final structure here. Can you tell me, let's just do one drop. Can this guy exhibit cis-trans isomerism? First of all, does it have a covalent bond with restricted rotation? Have. Does each carbon have different groups? Okay, each carbon different, correct? So yes, answer is yes. Now this is a case if they have all 4 different groups. So if I ask you, can you find out who is cis and who is trans? Just now we learned that you must look at the H's, right? Same side, that one same plane, opposite plane, correct? But now we only have one H. Can we determine who is cis and who is trans? Answer is no from our syllabus. In real life, cannot. But in our syllabus, well, right now, there's no need to identify who is cis and who is trans. But you just need to know having 4 different groups will allow you to undergo cis trans. That's it. Answer is yes. Can already. Yeah, okay. This is very simple. Oh, good. Yeah, okay. So we have gone through a few scenarios here. A normal scenario, alkene in a ring, normal ring, yeah, all that. Yeah, I know it's quite a bit, okay, but slowly do this. Okay, on page 47, there's a couple of examples. Yeah, I think I'll skip past this first. Okay, I want to talk about page 48. I think that's more important. Okay, on page 48, we're going to look at some formulas. How do we find the total number of cis-trans isomers? They can give you a very big molecule. Okay, but let me just start off simple. This dude over here. How many cis-trans isomers does this guy have? You raised the other guy already. So how many are there? How many cis-trans? It's 2 actually. Because I have one cis and then one trans which I deleted, right? One cis, one trans, answer is 2 long. Does that make sense? Yeah, remember, cis and trans are 2 separate molecules. Why are they separate? Can you remember the reason? Yes, exactly. You can't just twist this guy to get the same molecule. So cis and trans are completely separate molecules. Can you get it? Okay. So one cis, one trans, answer is 2. Okay, then there's some math to it. Anytime there's a double bond, there's one cis and one trans. So the formula, right, is 2 to the power of n. So for example here, n is the number of double bonds that can undergo cis trans. So here it's just 2 to the power of 1, that's why the answer is 2. Okay, if you have 2 double bonds, so how many isomers will you get? 4, not simple as that. Okay, your job here is to go and count. So let's look at this example question. Okay, I want you to determine how many cis trans double bonds there are. Okay, then just go and apply the formula, see whether you get that answer. Yeah, draw the molecule on the board, give you a bit of time to do. Okay, like these 2 carbons. Yeah, okay, you see this double bond, right? You need to check whether he can undergo cis trans. So for example, let's see, can this double bond undergo cis trans? You have to check this carbon and this carbon. Does he have different groups? No. No. Okay, 1 carbon each, same. So gone already. That's it. The moment one guy, right, violates the criteria, he cannot undergo cis trans anymore. Then you just need to repeat the same thing for the rest. Right? Is it? Wait, what's the answer? None, really. H, cannot. Same one. Like check this one, right? Okay, look at each carbon here. The one on the left, does it have different groups? Actually have. This one only has one carbon, but this one is like one whole chunk. Can you see that? Okay, this one, right, it joins with the rest. So this is one whole group. This is another group. So it's two different groups. Or you can clearly see, right, that this one has at least two carbons. This one has only one carbon. So it's different. Right? Is this carbon different? Invisible H and carbon already different, correct? So this one is considered yes. Yes, the rest of the thing is considered a separate, is a group by itself. It's whatever that's attached to this carbon. So you should put this carbon as like the center piece, and everything else is a group with respect to that carbon. So what I mean by that is, okay, if you look at this, another two carbons to take a look at. The carbon on the left, is it different? Yes, H and carbon different already. Is that it? Is it different? Yes, the whole thing that's attached to this red color group. So it's clearly different from this, right? Yes, so also different. How about the last one? It cannot because one H, this one it fulfills, right? This one's okay, but this one is two same H's, so cannot. So what's the total number of stereoisomers? 2? Oh, 4. Yes, okay, 2 to the power of 2, you must take all this, then you can get 4. So that's the answer to this. Okay, we have one final segment to go through, and then we'll be kind of done for today. Right? Okay, so just hang on for a moment. Okay, after we finish this, can take a short break. Okay, we're gonna look at this thing called enantiomerism. Sounds very weird, but all we're looking at now are mirror images. So you see this, right? It's just same side, opposite sides. But now we got normal image and mirror image. Now they are considered two separate. Okay, because I know, right, mirrors are not real. Right? The mirror image is like not real one. But then in this segment here, a mirror image is considered a real structure. Okay, so we're gonna take a look at how this works. Now, first of all, this is under stereoisomerism as well. Okay, you see, in the normal and the mirror plane, the spatial arrangement is different. Okay, so stereoisomerism got strands, but now also got enantiomers. Now, how do we visualize this? Okay, just now we had an article with this here, because that one had a mirror. Okay, but now we don't have a mirror, so try to visualize it. Okay, see this first page, page 49. I'm going to write down the definition first. If we look at an enantiomer, to form an enantiomer, we need to fulfill two criteria. Or more specifically, okay, take note of this. The mirror image must be non-superimposable on the normal image. What on earth does this mean? Okay, so I'm trying to unpack the word. If it's superimposable, then it can be qualified as. So the best way to visualize this is imagine, right, you have your hand. I'm going to put on my right hand. Then if you put your right hand and you look at your right hand in the mirror, try to imagine what that mirror image looks like. Let's just say in between me, there's a mirror. So I put my right hand here. Can you see what I see in the mirror is actually my left hand? Can you see that mirror, right? Okay, so what I'm going to do now is I'm going to take the mirror image, imagine I can pull that into reality, and I try to overlap them with one another. Superimpose just means overlap. Non-superimposable means cannot overlap. Can my mirror image of my hand overlap with each other? Okay, think about it. My right hand, the mirror is left hand. Okay, imagine there's a mirror through me. I take the left hand image, pull it into real life. I try to overlap them with one another. Can they be overlapped? Are they perfectly overlapped? No. My thumb is over here, but my thumb is over here. If you try to overlap your right hand and your left hand, they cannot overlap perfectly. So that's what we mean by non-superimposable. Okay, I know it's just weird here, but eventually this one you get over it. Okay, because this part is not too important. Then what is something, right, that can be superimposable? I want you to think of a tennis ball. A ball is round, right? The ball, if you put it in the mirror, it just looks like a ball, right? Can the mirror image overlap with the normal image? Yes, because it's perfect, right? It's just a freaking ball. So it can overlap perfectly. So that's considered superimposable. Then it will not qualify as an indentuber. Can see that? Okay, so what kind of objects are superimposable? What kind are not superimposable? Okay, a ball, why can a ball, right, just overlap each other perfectly? Any idea? Then how come my hand cannot? Let me give you another example. You see the conical flask in the notes? A conical flask, right? The mirror image is still a freaking conical flask, right? If you take this, you put it, you try to overlap. Can they overlap completely? Yes. You take a ball, you still see a ball, you overlap completely. But if you take my right hand, the mirror image is a left hand. Left hand and right hand cannot overlap one, as you can clearly see. Both palms facing up. Don't go and put both palms like this. Okay, why is that so? What's common between these two items that your right hand isn't? Yes. It's because they are perfectly symmetrical. That's why the mirror image can overlap perfectly. A right hand is not symmetrical. Your hand isn't symmetrical, so it is not superimposable. And the idea of symmetry is going to be quite important for this next part. Okay, so once you understand this part, okay, take a look at page 50. There's two criteria in order to be non-superimposable. So to be non-superimposable, number one, you must have a carbon with 4 different groups. Now, if you have a carbon with 2 same groups, can you foresee the problem? A carbon with 2 same groups may end up as superimposable. But more importantly, the carbon must have 4 different groups and there should be no internal plane of symmetry. And I'm sure you can see why already, because I already discussed that. Anytime a molecule, anytime an object is symmetrical, the normal image and the mirror image can overlap perfectly. Which is not what I want in order to be an enantiomer. So let's summarize this again. To be an enantiomer, you cannot overlap the images. And if you don't want to overlap the images, it cannot be symmetrical. The carbon must have 4 groups. Okay, a carbon with 4 different groups is known as a chiral carbon. Okay, we're going to use this term from now. Okay, next. Okay, how should we show this? Okay, we're going to show this thing called a stereochemical formula. Because remember, how does a carbon have 4 different groups? Can a carbon have a double bond and have 4 different groups? Because there are only 3 groups, right? So already out. How does a carbon have 4 different groups? What shape must the carbon be? Exactly. A carbon, in order to have 4 different groups, must have 4 single bonds. And that is a tetrahedral shape. Can you remember what I thought about for tetrahedral shape? Tetrahedrals are they flat, planar? No, okay, tetrahedral is non-planar. So in other words, I'm going to have to express the stereochemical formula. Only 2 bonds are flat, but the other 2 bonds one are sticking out, the other is sticking in. So that's how tetrahedral actually looks like. We have to draw this for this segment here. Okay, so turn over to page 51. I'm going to teach you how to draw a mirror image of the compound. So I'm going to use the one in the notes. Okay, this is what they did over here. Now you see in the notes, right? They write here page 3, correct? Never write the reverse. Always write C then H. This is a bit outdated. Okay, you are discouraged to write H3C. Never do that. Okay, so what's going to happen here is this. This is the molecule they've given us, and then we have this thing called the mirror plane. So imagine this is the mirror here. Okay, and how will you draw the bonds in the mirror? Okay, how will you draw the bonds in the mirror? Okay, let's start out with the normal bonds. How will the bonds look like later? Is it still like this? Okay, it must flip to the other side, right? Okay, notice the one at the top. It doesn't flip, right? Correct? Okay, then what else? Now, what is this bond actually doing? It is pointing outwards. Now, imagine this is the mirror. Imagine you look at the mirror, right? You point the, okay, this is my mirror is this marker here. Imagine, right, that my middle finger is pointing outwards, just like this guy here. How do you think the mirror image will look like? Will the finger be pointing outwards or inwards? Okay, if you point outwards, the mirror also point outwards, right? So whatever that is outwards must stay outwards. Does that make sense? it doesn't make sense for you to point outwards, then suddenly that guy can lean inwards. That's not how mirrors work. So over here, if the hydrogen is pointing outwards, here then, it should still be pointing outwards. Good. A lot of people assume that mirrors must flip everything. No. Okay, hydrogen cannot become pointing inwards. That's wrong already. So essentially what you're doing is you are just copying and pasting the same groups. It's just that flip the side. You see that? So it's actually not that difficult. Okay, so you just have to flip this. Yeah. So this is known as a mirror image. So you look at this, there's another thing here. This carbon has 4 different groups, right? So you can exhibit enantiomerism. Is it symmetrical? Yeah, alone. No, not symmetrical. That's why you can have a mirror image. So you can see this. From now on, you can also see an asterisk on carbon. An asterisk implies that the carbon has 4 different groups. So an asterisk will show a chiral carbon. Okay? So that's that. Okay, from there you can move on to page 50. Okay. The H no H for you. Sorry? Again, the bond must be bonded to O, not to H. So that's why I must bond to O. Okay, cannot write as OH. I mean, if you write as OH, then the O must still be bonded lah. Then your H must put like, you must squeeze here. Yeah. Okay, all good. Now, on page 52, we're going to introduce idea of enantiomers also. So, up until this point, we talk about mirrors, overlap this, overlap that. What was this stupid criteria? Then you are like, what's the point of this in real life? Right, okay, let's ask ourselves this question. What is the purpose of these kind of molecules? Okay, so there's a very special property. These guys are called enantiomers, correct? And enantiomers have a very special property, which is they can rotate plane polarized light. Now, this is a physics thing already. You do not have to know what a plane polarized light is. You just need to write the word plane polarized light. Can. And what does it mean by rotate? You doesn't matter. Don't need to know. It just can do this. So how do they rotate plane polarized light? I have a normal image and I have a mirror image. Now they are enantiomers of each other, right? They both can rotate this thing. Okay, don't you know how? But some properties here. When you have two enantiomers, they rotate plane polarized light by the same extent, but in opposite directions. So, I ask you this question. If the normal image rotates plane polarized light by 15 degrees, mirror image must rotate by how many degrees? Same extent, opposite direction. We look at the number first. If it's 15 degrees, this one must be what? Also 50. So that's same extent. Opposite directions means what? If this rotates in, let's say, the clockwise direction, this one must be anti-clockwise. Simple as that. Oh, that's it. That's the relationship between these two. It's a special power that enantiomers can do. Okay, that's a special property. Okay, so let's introduce another idea. If, remember, these are real structures. Mirror doesn't mean it's in the mirror, it's not real, it's real. Okay? If let's say I have the normal image and mirror image both in the same container, and they are in equal proportions. Okay, so let's look at this. Equal proportions of both enantiomers. Can you tell me what is the overall rotation? Okay. One rotate positive 15, the other rotate negative 15. But if I have equal of both in the same mixture, what's the overall rotation? 0 can cancel out, correct? Yeah, that's the idea. When you have equal proportions of two enantiomers, this is known as racemic mixture. Racemic mixture. Okay? So that is the second bullet point on page 52. Second and third bullet point. Yeah. Okay. So racemic mixture, I say again, is when you have equal proportions of two enantiomers. How about unequal? If you're asking me unequal, right? Doesn't matter. We don't really look at unequal. There's no name for that. But what do we say again? A racemic mixture is And does it have an overall rotation? No. No overall rotation. Now, we don't really use the word overall rotation. This is known as an optically inactive. So let's just say this. If I only have the normal image, it can rotate plane polarized light, right? So this is known as optically active. If I only have the mirror image, this is optically active. But you put two of them together, equal proportions. Overall, it becomes optically inactive. Can you get the idea already? Okay, so that's what we're about here. Racing mixture optically inactive. We'll see the application of this a few topics down the road. But right now, you just need to know what it is. Okay, so this one quite important. Okay, that's for the first few points. Okay, for page 52 at the bottom right, there's just a few things you need to highlight. They have identical physical properties. Okay, what are some examples of physical properties? Yeah, okay, melting boiling point is the same because they are legit just mirror images of each other. Like if one is 52 degrees Celsius, the other one also same thing. Okay, but there's only one different physical property, just highlight the exception. Is the rotation. We already said that the rotation is in opposite directions, right? So that's the only exception. Density, solubility, everything else, same. Okay. Now, chemical properties you can highlight, but not very important. What I want you to highlight, right, is different biological properties. It's not very important. Second bullet point you can ignore, doesn't matter. Okay, different what is biological property? You think of biological, you think of what? Anything to do with what? Anything to do with the body, right? Okay, yes. Okay, so for biological properties, is to do with the body. So now just now we ask ourselves, right, what the hell is the purpose of learning all this? What the hell is the purpose of an enantiomer? Create for what? Right, there's nothing better to do. Is it actually it's very useful because anything to do with the body is like medicine. So enantiomers are very, very powerful in medicine because there's a very common example. You know adrenaline, right? The shit that makes you pumped, right? You're excited. You see you want to chase your boyfriend at time. Excited. Right? Okay, but adrenaline, the mirror image, don't spell it out. It's called adrenaline, something like that. This thing, if you consume, is useless. This thing, if you inject, you feel pumped. So the idea is this: normal and mirror image, they have different reactions with the body. So they're quite important. They have tested questions of this before. This one's not fluff. It sounds like fluff, but it's not. Okay, so the thing is for drugs, same thing. Some drugs they are useful. Okay, then it's mirror image will cause you to die. It's quite scary. Yeah, okay. Yeah, so that's the idea for this portion. Okay, turn over to page 53. 53, very simple idea. I already mentioned cannot be symmetrical, right? Because if it's symmetrical, you're not going to have this overlapping, they're going to end up overlapping each other. Okay, so no internal plane of symmetry. Just look at I don't have to draw this out. Look at the structure of page 53. Can you see that that's clearly symmetrical? So despite both carbons, right, being chiral, you look at this, both criteria must be fulfilled. So even if your carbon has 4 different groups, it doesn't matter. If there is a symmetrical molecule, right, already, you won't manage to form your mirror image. Let's say, that's what this means. Nothing for me to discuss here. Okay? So can move on. Okay. Let's take a look at page 55. We are pretty much almost done already. On page 55, I need you to show me or let's just discuss which molecule exhibits enantiomerism, which one doesn't. Okay, so you can look at the first one, right? And discuss there. Okay, the one on the right cannot because obviously it has a internal plane of symmetry. The word internal is important because it's within the molecule. Okay, you see, does it have any chiral carbons? Okay, let's identify first. Anytime you identify a chiral carbon, put an asterisk sign. Okay, take a look. This, okay, usually the chiral carbons is in a more congested area. Like this carbon, is it chiral? No. All same hydrogens. This one a bit more congested. So let's check. One carbon. Is that it? It's a different group altogether, right? You must see, this one is the whole group with respect to this carbon here. Okay? This one is one carbon, but this one goes further than that, so it's different. Okay, but there's an OH, and then finally there's a invisible H. H, OH, CH3, and then there's this one very big thing, right? Okay, so all different. So this is chiral. So it's same set for this one. So even though they're both chiral, right, because it's symmetrical, they don't actually, they are not considered a chiral molecule. So it's unchiral. How about one on the left? Is it symmetrical in any way? No. But does it have any chiral carbons? Okay, if have, where is it? Is this carbon chiral? Is that it? Anytime you see a double bond, what's wrong with a double bonded carbon? This one I mentioned. You must have 4 different groups, right? A double bonded carbon will only have how many groups? 3 groups. So whenever you see a double bonded carbon, ignore it. It will never be chiral. We'll practice this in the next lessons tutorial. Okay, how about this carbon? Yes, this carbon is different because carbon, OH, invisible H, and CO2H, whatever this is. So all different. So that's the chiral center. So this one, yes, it is chiral. Okay. Yeah. Okay, let's move on to the next page. Okay, on page 56, we have the same formula again. Again, just now cis trans 2 to the power of number of double bonds. Same thing over here, normal and mirror. So we use the 2 to the power or something. Okay, so yeah, well, that's it. Okay, but we have an additional thing. Remember, cis trans and enantiomers, they are both considered what? They are both under the umbrella term of stereoisomers. Take note. I know there's a lot of new terms today. Stereoisomerism consists of both cis trans and enantiomerism. So let's look at this. If you want to find the number of cis trans isomers, 2 to the power of x, for example. X is the number of double bonds that can undergo cis trans. Then this one is 2 to the power of y. What is y? Any idea? You count the what? This is how you count the double bonds. Now you count what? You count the number of chiral carbons. So number of chiral carbons just 2 to the power of that number. Okay, but how do you find the total number of stereoisomers? If it's both, what should you do? Okay, 2y plus 2x, is it? It's not. Okay, so take note. It is 2 to the power of x plus y. Okay, it's not 2 to the power of x plus 2 to the power of y. The math just doesn't work. Okay, it just doesn't work that way. So just follow the form. Okay, so we can practice a bit. Okay, so you can turn over to the last page. I just need you to answer the first part. Okay, the second part, just now I skip one page, so we need to go back to that. Second part a bit more challenging. We'll do that in the next lesson. Okay, so your job here is to, first things first, I need you to draw this structure in skeletal formula. Give it a try. Okay, a tip I have for you is you go and count the carbons. Number 1, 2, 3, 4, blah, blah, blah. It might help. Okay. Yeah, I know it's a bit challenging because you just started. Okay, but must start early. Okay. Yeah, okay, the bracket means it's a branch separate from the main chain. Yes. Right. Okay, so what we have here. Yeah, I'll show you the technique first. Yes, okay, whenever you see brackets, they are branch. And once I label all these numbers, I have 7 carbons in total, right? What you can do is this. 1, 2, 3, 4. But my 5 isn't part of this, right? So let me branch it up. 5, then 6, 7. You can see that. So your carbon 4 is actually bonded to carbon 6. Okay, so I say again, 1, 2, 3, 4. Branch out 5, then you come back again, 6, 7. Okay, then from here, just add in whatever you need to add in also. Between 2 and 3, you see a double bond. You see, our numbering is very, very useful. You use this skill for the whole time you're doing this. Okay, so yes, after we have gotten this, what do we need to do next? Okay, how do we determine the total? They're asking total number of stereoisomers. Highlight the word stereoisomers. What are they asking for? Cis trans and enantiomerism. You need to look out for double bonds and carbons with 4 groups. Let's look at the double bond first. There's only one there, right? Okay, can this double bond undergo cis trans? Okay, look at carbon 2 and carbon 3. Does carbon 2 have 2 different groups? Yes. Yeah, draw the H's up. Is this different? Clearly different, right? Is this different? Okay, this H, then the moment it goes to a carbon, right, it's really different. But yes, it's actually this whole thing bonded to this. Right? Okay, so it's different. So yes, this is considered eligible. Okay, but that's only cis trans double bonds. How about enantiomerism? Any chiral carbons here? You see, we label all 7 carbons, right? Carbon 1, is it chiral? No. Okay, just now I already mentioned, find a more congested carbon. 2 and 3, do we consider? Double bonded carbons, don't consider, right? Because you only have 3 groups. We have 4 groups. Okay, how about carbon 4? It's a bit congested. Does it have 4 different groups? Okay, start from here. 1 carbon, 2 carbon, different group, different already, right? 4 carbon. Oh, sorry, 3 carbon. You see that? Okay, and then we have an invisible H. So it's 4 different groups. Okay, so this is chiral. Put asterisk there. So what's the answer here? Oh, what's the formula? To the power of x plus y. So it's 1 plus 1, right? It's 4. So we have 4 isomers. Now, part B, they ask you to draw the isomers, but that was a bit more advanced, right, for what we have learned today. So that one I'll only do in the next lesson. Okay, can. So with that said, okay, we have, today's lesson is very content heavy. Okay, but that's pretty much all for today. We have completed the notes, that's good. Okay, just the time. The next lesson, we still need the time to go through the tutorial. But because today we've gone through so much content, before the next lesson, you need to review all the content in this lesson first. Okay, the previous lesson, we talked about the introductory stuff. We won't actually be touching on that much. So just for the recording sake, whoever's watching the recording also, we only need to look at hybridization and isomerism in this topic. Look through those 2 again first, because after today, you're going to forget quite a few things. Yeah, I also got to see the recording. So just go and read through that first before the next lesson. Then next lesson, we're going to go over the tutorial. Okay, can? So, that's it for today. Yeah. Okay. Any last questions?